Hello, my name is Bernhard Heinloth from the Friedrich-Alexander-Universität Erlangen-Nürnberg, and I want to present our work about Luci, loader-based dynamic software updates for off-the-shelf shared objects. To motivate the topic, let's start with software development in a nutshell. We start writing the code, building, running, and then discovering the bugs in it. After patching up the issues, we have to restart the application, which is fine during development. However, if we have a productive application which has to maintain a certain state or connections, we rather want to avoid restarts. This is where dynamic software updates come in handy, which apply changes to the running process. This is a well-researched topic dating back more than 4 decades. However, the existing approaches usually require to change the source, or at least tools to process the source, have to use custom compilers, hence are restricting the programming language, or the approaches process the relocatable object files, or require even handcrafted patches on the basis of the ELF file, usually resulting in a binary patch file, which is then injected by a certain tool into the process virtual memory. The downside of those approaches is that they require extensive modifications on the software to enable dynamic updates. This is fine for a single project, but not if you want to reach generic updatability of user space with a multitude of different applications. Moreover, we usually don't build all our software on our own, but this is done by distributors like Debian, and they don't keep all old build artifacts like the object files, making existing approaches difficult to apply. In addition, the existing approaches are sometimes cumbersome to apply, introduce a certain runtime overhead, and require a specific order for consecutive updates. This is the reason why live patching nowadays is only used in the Linux kernel, but has not become reality in our user space yet. How can we overcome these shortcomings and pave the way for user space dynamic updates? Well, we must not require changes to the code or build side, but only use the resulting binaries to perform the dynamic update. And it should be easy to apply. Ideally, the update should happen without requiring any user interaction. To ensure everyday use, such an approach must not hinder the execution, especially not impact the runtime, and should focus on bug fixes which, in contrast to feature updates, need to be applied in a timely manner. Therefore, let's now have a look at our target, the user space applications. They are usually depending on libraries, especially the standard library, but since one most likely wants to avoid writing stuff like cryptography, compression, or parsing certain file formats, the usage of additional libraries is common. For example, the Apache web server has 6 external base dependencies, plus modules and their external dependencies based on the configuration file. If we have a detailed look at the first library, the Expat XML parser, well, it had 17 vulnerabilities only last year, many of them severe, fixed in 7 releases. This means only this library alone would require us to restart the web server or any other application using this library 7 times last year. And it is not only the Expat library. Since 2010, those few basic dependencies here had 81 severe vulnerabilities in total, requiring immediate action. But during the same time, the Apache application itself had only 14 of such vulnerabilities. Accordingly, it seems more beneficial to investigate dynamic updating in libraries rather than applications, which is the focus of this work on Luci. To be able to develop a solution, we first have to look at how libraries are linked. For system software, dynamically linked libraries are common. Here, the executable only contains the application code, while its metadata has a reference to the required shared object of the library. And additionally, it contains the path of a dynamic linker loader, also known as the runtime link editor or RTLD. When starting the application, both binary and the dynamic linker are loaded into the process virtual memory. Then the dynamic linker takes over and loads the required shared libraries as well. Since during static linking only local references have been resolved, the application has no knowledge where the library resides in this process virtual memory. Most likely the address is shuffled on each start. So for an application to be able to call a library function, then the dynamic linker has to perform the necessary relocations during the runtime before handing over the control to the application. Well, would it be possible to leverage this task for dynamic software updates of libraries? This question brings us to the design considerations of the Luci approach. Well, first of all, the dynamic linker already has meta information about relocations and access to the process virtual memory, hence being predestinated for performing the patching. Luci is such a DSU-capable dynamic linker. Then, since we focus on libraries, we have to acknowledge that infinite event loops are not that common there, having the advantage that functions usually return at some point. Therefore, there is no need to intercept active code in libraries. And finally, when investigating common bug fixes, it turns out that structural changes are very rare. They usually only add code for additional checks, like this example of a Expat CVE fix shows on the right. Well, in fact, only adding code is true for all fixes of the previously shown Expat vulnerabilities. These considerations lead to Luci's DSU support during runtime. During execution of an application, Luci will watch for modifications of the employed shared libraries. When a new updated version is installed on the system, Luci gets notified using inotify and starts to analyze the new shared object to see if it is compatible with the previous one. If so, Luci maps all non-writable sections into the process virtual memory, into a new unused memory area, while creating a memory alias for the writable sections. Hence, the data can now be accessed using multiple addresses at the same time. Therefore, pointers to global variables will stay valid. Then it updates the relocations. So from now on, every function call will be made to the new library instead of the old one. We have successfully dynamically updated the library. Afterwards, Luci will hide the old code while installing a user page fault handler, so we are even able to detect any access to the old code, for example due to function pointers. The idea of exploiting dynamic linkage has several advantages. First of all, we don't have to fiddle with machine instructions, but use the designated relocation interface, making it simpler and safer than other approaches which modify code in place. Since we have multiple shared object versions residing in memory, we do not need global quiescence in the system. Effectively, we do a task very similar to lazy binding. The approach does not require us to use a certain programming language or compiler. It works with Ada and Fortran shared objects as well, and you can use GCC, LLVM or whatever you want. And this approach does not introduce runtime overhead because there are no newly introduced indirections. The latest functions are directly accessed. Since this approach does not use ptrace or similar for accessing foreign process virtual memory, no additional privileges are required to perform the update. And it will always update to the latest version installed on the system, but it is not depending on subsequent versions, so even rollbacks are possible. We have implemented Luci as dynamic linker with sufficient glibc compatibility to run many common applications out of the box, so it acts as a replacement for the widely used standard glibc dynamic linker. Luci will automatically track modifications of all loaded shared libraries. If a change is detected, Luci will check if the writable sections are identical in terms of alignment, layout and contents, that the initialization routines have not changed, and the interface and types like enum and structs match. For this, it can also use the debug information when available. However, a hash of the required var fields is sufficient to check the compatibility, since debug information is not required for the update itself. Here we rely solely on the ELF metadata. After mapping the sections into the process virtual memory, first, local relocations are applied, before updating each global offset table in the process, and finally, after some time, preventing unauthorized execution of old library code. But in case Luci finds incompatibilities, the user can get notified about the requirement for a manual restart, while the application continues with the old code. To evaluate the described approach, we want to focus on real-world scenarios, since this is the focus of Luci. One target is the previously shown Expat library, which is quite popular. There is a high chance that you use it in your daily life. Expat is in active development and had several vulnerabilities in recent years, so we have a worthwhile target for dynamic updates. For a realistic scenario, we will first test Luci on its official releases, not only on single patches. We build each release in an isolated standard environment according to the documentation and do not apply any customizations. If we let Luci analyze the compatibility of all resulting shared objects, we see changes in each release in comparison to the previous one. For example, a different node section due to the changed build ID, but this does not hinder updates at all. However, in 2 releases the initialization functions have changed, which we categorize as an incompatible change, since this could lead to an invalid state. While first and foremost code and read-only data change in each release, we also see several releases with different writable sections, which prevent updates. Obviously, these changes are reflected in the debug information as well. However, on 2 occasions only dwarf has a red dot. This is due to changed record types. Here only new enumeration values have been added, but Luci is rather pessimistic and still marks it as incompatible. And if there is at least one incompatible section in a release, Luci won't perform an update. This means for updating all releases consecutively, we would have to manually restart 9 times. However, for the majority of the releases, 17 in total, the Luci approach could perform the updates automatically. To verify this claim, we will use the Expat test suite. It covers the whole interface and all the functionality provided by the library, and receives regular upgrades if vulnerabilities are found in the library. Therefore, this makes it a great target for evaluating Luci, since it would clearly highlight any incomplete update. We use the latest version of the test suite, executing all tests in an endless loop, while skipping tests which would cause fatal errors like segmentation faults on older versions. As before, I want to emphasize that we do not apply any adjustments to the source code or build chain. When executing the test application 27 times with each version using the default glibc dynamic linker, we can see the number of successful test cases increases due to the fixes introduced in each subsequent release of Expat. But with Luci, we are required to restart the application only 9 times. This is due to the previously shown incompatibilities. However, as Luci has predicted, for all other releases, dynamic updates can be applied, and even the 10 most recent releases in a row. The output of the dynamically updated test application is identically to manually starting it with each release using the default system dynamic linker. And in no case there was an inconsistent state or abort of the application. Well, but how does Luci perform on distributable binaries, which sometimes use different build environments or update build tools for creating new packages? To evaluate such off-the-shelf files, we backtest all Expat shared objects released in Debian Buster, hence simulating the historic package updates. One remark: since we were not able to retrieve debug symbols for each package in the snapshot archive, we fully ignore debug symbols here. When analyzing the packages, we can find several releases in the archive, some with major changes, but also a few minor or even two identical releases. And the version number first increases before it gets fixed to version 2.2.6 in the stable phase of Debian Buster, while still having changes despite the identical version. When now executing the test application, we can see an increase in the successful test cases, even in the stable phase. This is due to the Debian team backporting important bug fixes to their version while maintaining a stable interface at the same time. As the analysis suggested before, Luci is in fact able to update most releases during runtime, and all of them into a stable phase, hence when Debian version is intended for a productive operation. And this is not an exception, but true for other distribution versions of Expat as well, like Debian Bullseye or the two most recent Ubuntu LTS versions. We are able to dynamically update most releases, and more important, all of them during the stable phase of the respective version, usually consisting of important bug fixes. And even when testing other libraries in a similar manner, like from the Apache example, we can apply most releases, either vanilla or backtesting, without restarting the application, except for OpenSSL. This is due to function pointers in writable data, but could be solved with proper software engineering. And I want to emphasize that in all cases, even in OpenSSL, Luci was able to maintain a valid state for the application, no matter if a dynamic update was applied or not. With that, I'd like to summarize this approach. We have presented Luci, a dynamic linker loader with DSU capabilities for libraries, which is able to handle shared objects in binary form as they are distributed today by adapting the techniques for dynamic linking. It runs fully automatic, no user interaction is required for the updates. It does not cause runtime overhead and is sufficient for most bug fixes. Luci is licensed under HGPL and available on GitHub. We hope that our contribution can help to pave the way for dynamic updates in user space. Thank you for listening, and I'm happy to take your questions via Slack or mail.